Hi everyone and welcome to my talk. My name is Yasmina and I am a PhD student at TU Eindhoven. On behalf of my colleagues, I'm going to present our work submitted to the M&M-2 challenge, a late fusion unit with GAN-based augmentation for generalizable cardiac MRI segmentation. Right ventricular structure and function assessment is vital for the management of most cardiac disorders. The first step in performing the assessment is typically obtaining an accurate segmentation of the heart cavity. However, RV segmentation is challenging due to the complex heart motion and RV anatomy. In fact, RV segmentation approaches underperform due to unclear borders caused by blood flow and partial volume effects, presence of trabeculations with the same gray levels as the surrounding myocardium, the complex shape of the RV that varies throughout the volume, the significant influence of pathology, and the use of short-axis image orientation, which is efficient for the analysis of both heart ventricles, but is not fully optimized for the RV. In addition, research has shown that automated segmentation methods do not generalize well to unseen data. Since data in medical imaging is scarce, algorithms are trained and evaluated only using samples from single centers, similar scanner models, and imaging protocols. This impacts their usability in clinical settings where the adaptation requirements are vital. In this work, we address the problematic aspects of RV segmentation in both long-axis and short-axis images by applying a number of steps aimed at tackling the following issues. Variations in the field of view caused by changes in resolution and voxel size, which directly affect the size of the heart as well as the visibility of the background tissue. Variations in contrast and intensity that present additional challenges to deep learning algorithms. Limited data that hamper the training of deep learning algorithms. Segmentation of basal and apical slices that are particularly challenging to segment due to their complex structure and size. And the presence of pathology altering heart tissue intensity levels and shape that can drastically affect the segmentation performance, especially of the RV. We train and evaluate our approach on the data shared in the M&M-2 challenge. There are 360 subjects in the dataset containing various right ventricle and left ventricle pathology. 160 of these are available for training and are completely labeled. 40 are used for validation during development, and lastly, 160 are used for testing and are unknown to us. All subjects contain both short axis and a long axis slice with the aim to segment both. To address the above challenges, we propose a synthesis and segmentation pipeline designed to minimize the disruptions caused by variations present in multi-vendor, multi-site, and multi-disease data. To reduce the effect of variations in the field of view and heart size, we introduce a heart region detection module. We utilize a conditional synthesis approach to generate a large number of highly realistic images with variations in contrast and heart appearance as well as pathology. We further emphasize on basal and apical slices and outliers that are underrepresented in the dataset. Finally, to regularize the segmentation network performance and produce a robust model, we introduce a late fusion approach to training. The first stage of the proposed pipeline consists of automated heart detection, where a bounding box is detected that surrounds the complete heart in short axis and long axis images. The detected bounding box is used to crop the input images for training the segmentation and synthesis as well as at inference time. The network is trained by computing the smallest bounding box from the available labels that fits the entire heart in the field of view. We use a simple 5-layer regression-based CNN with the output consisting of 6 continuous values used to adjust the parameters of the bounding box that is initialized at the center of the image. These parameters consist of x and y directions of the center of the initialized bounding box, lower left corner, as well as the scaling factors for the width and the height of the initial bounding box. We observed that the addition of the bounding box detection module significantly aids in decreasing the HD, or Hausdorff distance, particularly for short-axis images, as it largely eliminates false positives appearing due to large and varying field of view. The training data for long-axis and short-axis segmentation networks is further boosted using the image synthesis module. The synthesis module includes a ResNet-based encoder coupled with a mass-conditional generator that uses spade normalization layers throughout the network architecture to preserve the anatomical input label map. The ResNet encoder is designed to extract style information of the input image and provide it to the spade generator that preserves the content of the input label map. We also apply label manipulation to introduce anatomical variations in heart geometries of the synthesized images. Upon training the image synthesis model, random elastic deformation and morphological dilation are applied on the segmentation masks to create new labels for synthesis. Subsequently, the deformed labels paired with its corresponding synthesized image are used for data augmentation. Inspired by multimodal CNNs and late fusion approaches, we modify a typical unit to include multiple encoder layers. Each encoder path processes a different transformation of the same image at the input, which are designed to address variations in contrast and intensity homogeneity. In total, we use 6 different transformations, which means having 6 different encoding paths. By exploring the provided training and validation sets, we observed that not only the data acquired from different vendors varies in contrast, but that the presence of pathology influences tissue visibility and occludes tissue boundaries. Applying image appearance transformations can help with improving both the contrast and visibility and put more emphasis on tissue shape. We standardize the intensities of images to those representative of each scanner vendor using histogram standardization. Thus, for each image, we generate its 3 counterparts, standardized to the landmarks extracted from GE, Siemens, and Philips acquired images. Then we use edge preserving filtering to emphasize the shape of the heart cavities and discard high-frequency features, as well as combination of solarization and posterization to emphasize edges and flatten the image. Finally, we use the Laplacian to highlight the regions of rapid intensity change. Our hypothesis is that processing the same image represented by different features leads to the network being more robust to typical variations observed in multi-site, vendor, and pathology-influenced images. Our synthesis strategy relies on the RV end-diastolic and end-systolic volume, which we observe to be largely influenced by the presence of pathology. Within each vendor set, we synthesize more underrepresented cases scattered at the tail of the distribution by applying more deformations on their ground truth labels. To balance all of the subjects, we synthesized 1,000 cases per vendor, which include 50% outliers and 50% of other cases. To increase the occurrence of basal slices, we used the labels of 3 most basal slices of all cases and randomly deformed them for image synthesis. We do this because the ratio of the number of midventricular and apical slices to the number of basal ones is not balanced in the short axis stacks. The basal slices may not be frequently seen by the segmentation network during training, and this could account for network failure on those slices. Here are some examples of our synthesis approach. First, we see 4 deformations for a normal case of a healthy subject, and then 4 deformations for an outlier case, which was determined through the inspection of the RV end-diastolic and end-systolic volumes. On the right-hand side, we show random cases which have been generated in the style of different vendors. We can observe both variations in anatomy and appearance. We compare the proposed approach to a number of different models containing a different set of pipeline components proposed in this work to evaluate where the most improvement is obtained. Our baseline is a regular unit with histogram standardization, further boosted with the addition of bounding box detection, which already improves the results. We further add intensity transformations and synthetic data to the training, which helps the model in handling examples with unclear boundaries, low tissue contrast, and distinct presence of pathology. However, the major improvement is seen with the employment of late fusion model combined with synthetic data, which allows the model to extract more variable image features through different encoding paths, processing different representations of each image. The addition of synthetic images introduces more examples of hard cases and helps with network regularization and generalization. On this slide, we visualize the improvement in performance of the tested models due to different model components, with the best output in the last column obtained from the proposed late fusion model and synthetic data augmentation. We observe a significant improvement in the RV segmentation, but we can also see the impact of late fusion and training with synthetic data on tough cases with unclear boundaries. Similar can be observed on short axis slices, where slices closest to the base of the heart are typically problematic to segment but are improved using the proposed modules. Finally, we obtain quite competitive results in terms of dice and Hausdorff distance on the independent test set. To summarize, in this work we propose a late fusion pipeline for segmentation aided with GAN-based synthesis for augmentation to improve model robustness. Our pipeline consists of the heart region detection to handle variation in the field of view, as well as a mass condition GAN for synthesizing morphologically deformed heart shapes. These are used to augment the underrepresented pathological cases and introduce more examples of basal slices to the training. We additionally use contrast transformations to handle intensity variations and design our network to extract more variable features through different encoding paths under a late fusion approach. In conclusion, We discovered that having a diverse dataset plays one of the main roles in obtaining a robust and generalizable segmentation model, which can be achieved through smarter augmentation and synthesis when data is scarce. Thank you for your attention.